Well, let's start reviewing control volume approach, and which include the conservation of mass, momentum equation, energy equation, and the second law of thermodynamics as well. Right? So if you open any fluid mechanics book, they will always start with the definition of what is a fluid and how is it different from solid mechanics. The difference is that a fluid cannot withstand shear stress. The moment you shear it, he will move. Alright? But a solid, a rubber or steel or whatever, if you basically shear it, he will deform and then stop, right? A piece of rubber, you can basically shear it, it will deform a little bit and then it will stop. It takes more force to push for the next degree, and then even more force to push for the next degree. If this was a piece of wood or a piece of steel, you really need to spend a huge amount of force to make even the slightest change. This is not the case for fluid. Even for the most viscous fluid, still in principle, you shear them. By shearing, I mean you're not pushing on them, you are moving parallel to them. If you are shearing them, they will not resist the movement and they will move. Alright? Of course, the strain rate, or basically how quickly do they move, is different if they are ketchup or water or crude oil, right? The more viscous, the more force it takes for them to actually move faster. Right? And in this slide, I just would like to remind you that the molecules, if you go to the molecular level, say water as liquid and water as steam. For water, in both cases, if we open a microscope and look at those molecules, they're exactly the same. H2O molecule as water and H2O molecule as gas or vapor or steam, it's exactly the same. So why they are different? For example, a liquid, water, will always have the same volume and seem to be incompressible. You cannot compress it, or it's very, very hard to compress it. It takes tons of pressure to squeeze the volume of the water, right? But steam, if you have this much volume of steam, you can compress it, right? That's how steam engine work, right? So why the same molecule behave one time as incompressible, the other time as compressible? And the secret lie in this graph. What is this graph? This is, imagine a molecule, I and J, and they have a distance between them R, and this Fij, that's the molecular force between those two molecules as function of R, the distance between the two of them. So that force, forget about where did this come from, but you'll take this in grad school, but let's see that flip of the sign. It was plus here and minus there, meaning that at very short distance, if you try to push them against each other, that is a repulsive force. They will say, no, keep him away from me. But if they are far away from each other, they pull each other, they attract. Alright? So the difference between liquid and gas is that liquid is already here. They already are very close. You cannot really allow them to get even closer than this. But for gases, water vapor, for example, or steam, they are far away here. They are so far away to the extent that for a gas, air, for example, the molecules kind of don't even see each other. They hardly meet another molecule. Okay, only when they start, they travel a long distance before they collide. By long distance, I'm talking about nanometer. But that's really long distance compared to them. So that the distance that they travel on average to hit another molecule is called the mean free path. And so that's a really long distance, right? So why? Because when you think about it, what's the difference in density between water as a liquid and water as vapor? The difference is almost 1,000 times, right? Water density is what, like 997 kilogram per meter cube, and the air or vapor, we are talking about 1 kilogram per meter cube. 1 kilogram per meter cube, 1,000 kilogram per meter cube. In the same meter cube, there are 1,000 times more mass, 1,000 times more molecule. So per unit length, it's like you are packing 10 more compared to 1, right? So 10 molecule for liquid, 10 by 10 by 10, that make it 1,000 times more than. So that's the reason, right? So the difference between gas and vapor is basically that the intermolecular forces are different because the spacing is different. All right. So then the gas, the ideal gas, the gas that's here, it follows this equation. P equal rho RT, right? That's the perfect gas. But what if the gas is not really here? He's pushing toward this. How would that happen? How did they get closer like this? What will make the air, rather than being here, start getting closer together?
Pressure.
Temperature need to go lower, or the pressure need to go up. So that's how we liquefy gases, right? If you want to ship natural gas to another country and you don't have pipeline, so Russia send all the natural gas by pipeline, but other countries in the Gulf, in the Persian Gulf, they basically liquefy their gas, put it in a big tanker, and then ship it, so that they can put enough mass in the same volume. So how does this work? Because if you pressure it, you are getting them closer together, right? To the extent that not just they become almost liquid, they become liquid. You can push them all the way until nitrogen is liquid nitrogen, right? And how is that working with temperature? Why, if you cool them down, they become liquid too?
Less energy.
And so the temperature, actually, when you think about it, what is the temperature? If I had this air in this room at 70 degrees Fahrenheit, hopefully, no, it's not, probably 85 or something. So what does it mean that it's at 85 or 70?
It's releasing a lot of energy.
It's really, when you think right, when you think about it, that molecule has nothing to do but his kinetic energy, right? He also has some vibration energy inside it. But the point is, when we say this gas is hot, this guy is at high temperature, what we mean is that he got more energy, right? So he's moving, he's bouncing so quickly. So when we cool him down, when we take this energy from him, he's like, right? He was like flying so quickly, and he took his energy, and they drop. And when they drop, they get into a smaller place. They become almost liquid, right? So in the way to become liquid, in some application, when the temperature is really cold but not cold to become liquid, and the pressure is so high but not high to become liquid, you are not dealing with ideal gas. You are dealing with something called real gas. So real gas will have a little bit more complicated equation than this ideal gas, right? And so this is any gas that you push him toward the way to become liquid, he will start to become real gas. And so it depends on your application to tell yourself, are we good enough with this? Is it okay? Let's keep our calculation like this, or no, the temperature is really low and the pressure is really high. Let's move to the real gas equation. So in this course, no matter what is the temperature or the pressure, we are doing ideal gas, right? For the rest of the course, forget about this. It's P equal rho RT. We will just take the easiest way out, and we will call our gases ideal gas. But know that if the pressure is really high, if the temperature is really low, you may deviate from the ideal gas. So for example, that's why in steam, in thermodynamics, why you don't use P equal rho RT? I just said that the steam is a gas. Why you're not using, you keep using the steam tables, and why you don't use P equal rho RT? Right, it's because the steam is not really very, very superheated to the extent that it's really an ideal gas. So the air in this room, ideal gas, why? Because here at 85 Fahrenheit, he's very far away from his liquid state, right? He went, in order to make nitrogen liquid, the temperature needs to be really low. That's why they love liquid nitrogen for cooling, because the temperature is very, very low. But at room temperature, the nitrogen and oxygen is already basically superheated. All right? Of course, when we deal with rocket engine at the end of the course, and we need to carry our fuel with us and our oxygen, because in a rocket engine, the difference between rocket engine and jet engine is that you have to strap your liquid and your oxygen on your back. There is no air. All the other jet engine, all the other airplane, they breathe air and they just carry the fuel, right? But rocket engine, you carry both of them. So guess what? They carry the oxygen and the fuel, which is most of the time hydrogen, as liquid, right? Because otherwise, it will take huge tank to carry them at. Very good. So we said we are going to follow basically ideal gas, B equal rho RT. And the enthalpy H and the internal energy U is actually a property. You need to get the enthalpy, you need two properties. You need to know the temperature and say the pressure. Remember in the steam table, you need the temperature and the entropy, or the temperature and the specific volume, and then you can put your hand on the enthalpy. So it should be function of two properties. But we will actually deal with just the H is function of T and U is function of T. All right? So thermal perfect gas. And not only that, but we will also have, so by definition, dH is Cb dt. And Cb, that's the specific heat at constant pressure, right? And Cv, that's the specific heat at constant volume. That's U and that's H. So by definition, du is Cv dt and dH is Cb dt. What that mean? That means that if you want to get what's the difference in enthalpy as we heat the gas from 100 degree to 200, you need to integrate over Cp. You say Cb dt and you integrate. We are not going to do this. We will just assume constant Cp and constant Cv. And in the exam paper on the cover, you will see for air Cb is 1004.5 joule per kilogram Kelvin, for example. But know that Cp is really function of temperature. You cannot just take it outside the integration and say, well, then dH is Cb delta T. That's it. That's only if you assume constant Cp and Cv. All right? So in real life, it's not. And in real life, in really complicated problem, you have to take that integration into, yes, you can deal with constant Cb, but only from 100 to 110. We'll use that Cp. And then from 110 to 120, you will use another Cp. And from 100, so it's the same concept. So we will learn that concept in this course, that basically over our range of interest, we just have one value of Cp. And we'll deal with it. All right? And the Cb and Cv is actually, Cv is R over gamma minus 1, and the Cb is gamma R over gamma minus 1. So when you divide the two of them, R and gamma minus 1 will cancel, and you will end up with gamma equals Cb by Cv. By definition, gamma, and that number is very important for us in this course, the specific heat ratio, is basically 1.4 for air. All right? So gamma is the ratio between Cb and Cv. If you open those other textbooks that I told you in the library, you will find sometime that gamma is K. In other textbooks, they may use K as the specific heat ratio. Right? So some textbooks use K and some use gamma. But anyway, this guy will show up in all the equations to the extent that the appendix C's at the end of the book, for every chapter there's appendices that we can use for solution. You will find in every chapter there are 3 appendices for 3 gammas. So the difference would be, well, this is the table for gamma 1.4, this is for gamma 1.3, this is for gamma whatever, all right? Very good. So now the pressure. So you know there is something called the absolute pressure and something called the gauge pressure. The difference between the two of them is that P atmosphere is subtracted. So let's say in this room the pressure here is atmospheric, 101 kilopascal, 101.325 kilopascal. Let's say that the pressure here, for whatever reason, someone pressured the air in this class and it's not 101.325, it's 102. All right? That's the absolute pressure. All right? So if I ask you what is the gauge pressure in this room, you would tell me 102 minus 101. So the gauge pressure would be 1 kilopascal. Right? The absolute pressure is 102, and the gauge pressure, how high you are from the atmospheric, is the gauge pressure. So I remember taking my fluid one of my biggest problems as a student was when to use gauge pressure and when to use absolute pressure. I mean, that was a horrible problem for me. I couldn't really answer. And I spent a lot of time with my TA trying to understand. So when do I use gauge pressure and when do I use absolute pressure? All right. So here is when. And when you are using equation, the ideal gas equation, P equal rho RT, let me ask first, what temperature should you use? The degree C or Kelvin? Kelvin, the absolute. That's what will remind you. If you use the absolute temperature, then it must be that you should use the absolute pressure. So when it comes to the equation of state, use the absolute pressure. And when you think about it, the equation of state really need the actual pressure, the real pressure, not the difference between that pressure and the pressure outside. Who cares about the pressure outside? So the equation of state require you to use the whole pressure, which is absolute pressure. All right? So then when we use the gauge pressure, why is it useful for us? It's useful when you are doing force calculation. When you are using momentum equation to say find the thrust on a rocket engine like this. Anytime you use the momentum equation to find the forces, you have to include all the forces acting on that control volume. Whether that control volume is a jet engine or a jet ski, that's your homework. So your homework, we'll see it at the end. Your homework is a jet ski and you're trying to find the force that basically that engine generate. So you want to put the forces. So what are the forces acting on a jet engine sitting on a test stand in your lab you are trying to test? One of them would be the pressure forces, right? So you will have to put the pressure at the exit. I'm calling it B exit. Let's call it B exit. All right? B exit, area exit. That's the force, because what's the unit of the pressure? Pascal, which is Newton per meter square. So that's why when you get the force, the pressure force, you multiply by the meter square. You multiply by the area. So you get the force. So the pressure force is the pressure time its area, right? So I will put B exit, area exit like this. Okay? And by the way, is the B exit atmospheric, higher than atmospheric, lower than the atmospheric? What do you think?
Because it has velocity. I don't think that's right. I think as soon as it leaves the end, it goes to atmospheric.
So that's a good point. That basically he will need to feel the outside, and the outside the atmospheric, right? Anyone? So I had lower than atmospheric because it has velocity, and high exactly atmospheric because he need to feel what's going outside and adjust itself. Anyone saying higher? Anyone? So if this was subsonic jet, fluid 1, it has to be atmospheric. There is no question that it has to be atmospheric. He would feel the pressure immediately. But supersonic flow has a mind of its own. He can afford to be different. All right? He can actually leave lower or higher than the pressure outside. But eventually he needs to feel the pressure outside. That's why those diamond, we'll spend one chapter trying to understand those diamond trail. But those diamond trail behind that airplane flying, it was because of this. He was trying, oh, I'm higher than the atmosphere. Let me get lower. Oh, I did overshoot. Let's go higher, lower, higher, lower, until eventually he settled down on the atmosphere, and he basically just become atmospheric.
So as long as the problem says it's subsonic, we're good at P.
Right.
E equals atmospheric.
Right. But really subsonic. Really subsonic. So actually forget about this. It's like fluid 1. So here in this course we can afford to be different. All right? So this B exit can be either higher or lower than atmospheric pressure, right? It can be either higher or lower. So now the other side I have to put B atmosphere, right? Is B atmosphere only on the front?
All around.
It's actually everywhere. Right? And so this and look at this. You know, over here in this geometry, if I'm writing the x momentum equation, because the momentum equation can be written in the x direction or y direction. In the homework, you will choose what direction you write to get the stuff. For example, here in this example, if you want to get the thrust, you are interested in the x or the y. You want the x, right? You want the x momentum equation because that thrust will show up in the x momentum equation. So now you would say, then I don't care about this pressure, right? Because it's vertical. But you care about the component of this guy. So now I have to worry about all this geometry and all those x component wouldn't it be nice if I can forget about the B atmosphere everywhere? It would be nice, right? If I just say to myself, let's have B atmosphere everywhere, cancel it out, but B exit is not B atmosphere. Don't worry, we will just use B exit gauge. So by this, we are basically canceling B atmosphere everywhere, including the part in the exit that's atmosphere, all right? And of course, including also this guy. So by using B exit gauge, rather than the whole B exit, only the gauge part, then you basically give yourself the peace of mind that you don't have to worry about B atmosphere everywhere. They cancel out. And by saying B exit gauge, I don't necessarily mean that B exit is 120 kilopascal so that the gauge is 20. It could be 90 kilopascal. And the gauge pressure in this would be minus, right? So B exit gauge could be plus or minus depending on is B exit higher or lower than atmosphere. But this basically gave us the peace of mind that we don't have to worry about B atmosphere. So that was pretty good when I was undergrad, except the homework problem came with this rocket went to space. Now I'm lost again.
Yep.
What should I do now? Should I use absolute or gauge in space?
Doesn't matter.
Excellent. It doesn't matter because, but you know, you want to memorize something. You want to memorize the rule. I'm like, where is the rule? What's the rule? Well, if you go to space, you don't have to worry about the atmosphere because everywhere it's zero. The ambient pressure is zero everywhere, right? But you got the drill. So you use the gauge when you want to cancel the atmospheric pressure everywhere around this guy, and use the absolute in the equation of state, right? When you say P equal rho RT. Very good. The viscosity and the boundary layer. So in this course, you will see me drawing velocity profile like this. Okay? So basically the velocity is uniform throughout the nozzle. I mean, the area is getting bigger or smaller and the velocity is changing, but I will plot the velocity profile uniform all over the place. That's a simplification. That's not the true thing. If I zoom in, see near here near the wall, you will see something like this. This is called the boundary layer. And you will learn about this in 4273. That's the, say, let's call it fluid 3 then. The 4273, that's experimental fluid dynamics. You will hear about how to calculate this. This is actually very important when it comes to the friction. All the friction loss with the wall happen in this place. As a matter of fact, the flow on top of that boundary layer can be considered as if it's inviscid or frictionless. There's no friction on top of that. All the friction is located near the wall. All right? And so when you think about it, so why it's sticking to the wall like this? Why the velocity here need to be zero like this? Why the wall is holding it?
Because it's not perfectly smooth.
Right. Right. If you look to the, if you zoom in here again, let's magnify our microscope and look here. The wall, no matter how perfect your machining is, even if you did the best polishing in ever invented, the wall on a molecular level is basically this rough. Those blue dots, that's my impression of molecules. So here is the air molecule. So they cannot afford to go with different velocity than the wall. Why? Because they are not really on the wall, they are in the wall. Exactly. So then the first layer in the wall is kind of stuck with the wall. If the wall is an airplane moving, they are moving with that velocity. If the wall is a pipe wall, they are stuck in that wall. But then how about the next layer? They are not stuck in the wall. Why they are slowing down? That's
Molecules are being bound to the other ones.
and that phenomena is called the viscosity. So actually when you think about it, what is viscosity? Why the flow is viscous? Why does the flow stick to each like honey or ketchup? Why it's so like you spend a lot of time trying to get the ketchup and doesn't want to come? Why? Why it's so viscous? It's because those layers next to each other, they communicate very well. The molecules basically are kind of like stuck together. Not really stuck, but they communicate pretty well between each other. All right? So for gases, since this course has to do with compressible flow, which is mainly gases, we said the molecules are not sitting next to each other. We said, as a matter of fact, those molecules spend a lot of time away from any other molecule, and every now and then they hit another molecule. But if they hit so frequently, then they feel the velocity of the layer above them, right? So if a flow from the layer on the wall, if the molecule from there go and hit the molecule on top, he will actually slow him down. While the molecule from the above layer will actually speed the guy that's coming from down. And that's what creates this velocity profile. And if the flow is very, very viscous, what do you expect to happen to this boundary layer? Will it get smaller or bigger? Bigger. It has a lot of layer feel it. So imagine the difference then between water and honey is that water will have very small boundary layer. We're talking about few millimeters. But honey will have huge boundary layer, right? Because the layers are very well connected to each other, right? That's when we say the fluid is sticky. So the viscosity will be measured by two properties. The dynamic viscosity, that's mu, and that's when people just want to say viscosity. That's what they mean, the dynamic viscosity. And the unit is Pascal second. And then there is the kinematic viscosity, or nu. That symbol nu. And nu is actually mu over rho, right? I remember when I was undergrad, my Latin was not perfect, so I wouldn't really understand which is mu and which is nu. How could I make the difference? And then I realized that mu is like an M, that's mu, and nu is like capital N, so that's nu. So anytime I look to that symbol, I actually see a capital N in front of my eye, and I almost say nu. And when I look at this guy, I basically say, I see an M, and then I say mu, right? So that's your mu, and that's your nu. Okay. The engineering units is Poise and Stokes, right? Very good. Question so far? So what I'm trying to say then is that we will ignore this layer for the majority of this course. Only when we go to chapter 9, that's when we will consider flow with friction. And even in that chapter, we will basically just calculate the friction loss. But we will still basically care about the majority of the flow, not that small part near the wall. Yes, Yang.
So say you have something pushing from behind it.
Like a piston?
Yeah. So what would the velocity be just where it's touching the piston? Would it be just the speed of the piston?
So if the piston is moving like this in a cylinder, the question is, what is the velocity profile will look something like this. So we will actually deal with this in chapter 2. We will see a piston moving and what will happen. But basically everyone in front of the piston doesn't have a choice. They got to move or go into the piston, which they can't. Right? I mean, they can't go into the piston. So the piston will just move everyone in front of it. All right? But then over here, what do you think happened here? Are a little bit far away from the piston.
They're going to have a bowl.
So Tim is saying same thing. So Tim thinking that if that piston move, everything should move. Tim is thinking fluid 1. And that's true. If this was water, a piston move, the whole thing move. But if this compressible flow and that piston move, we'll see the answer in chapter 2. All right? You will see this next week. We'll spend time understanding how much difference does it make that the flow is compressible. All right? But basically, in compressible flow is like this fluid is a piece of stick. It's a stick. A stick of wood. Imagine if you push that side of the stick of wood, what will happen to the other stick side, the other end? The whole thing move as one piece. That's what incompressible fluid does, but not compressible flow. Right? Okay, so now to review the control volume approach. This is what you had in fluid 1. So basically, the difference between a control volume and a system is that a system is when you care about a bunch of molecules. You know them by name, bunch of students. You are tracking those students, as they are going outside the classroom, start going to their cars, moving with their cars to different places. At every minute, every time, every moment, the number of those molecules, number of those students is conserved. they cannot disappear. They cannot, and not a new student can be created, right? But if you care, and that's the case in most engineering applications, we don't care about air molecule, or we care about a volume, our jet engine, our classroom. How hot does it get? Huh? You have a space, and you care about that space, its mass, its forces acting on it, its energy. So that classroom, that classroom can see an increase or decrease in the number of students into it. All right? So the physics of a system is pretty simple. For example, dm by dt for a system is 0, right? But dm by dt for a control volume is it 0? It actually can be plus or minus, depending on what? The input and the output. How much is coming in and how much is coming out, right? That is actually the second homework problem that you have. You have an air tank fed by a compressor at a certain flow rate. The outlet, a toolbox or a tool or something using a certain flow rate to run, and he's asking you about what happened to the mass inside that tank. Will he build up the mass or the mass decrease? So what do you solve a problem like this? The continuity equation, right? So the continuity equation basically, and the momentum equation, energy equation, they are all actually copies of one big equation. It's called the Reynolds transport equation. All of them are basically just telling you what happened to a property that you are tracking it over that control volume. What happened to that property? Will it disappear, decrease, or increase? So this is a fancy name and a fancy equation for something that's really simple, all right? When I was a student, I loved to write this equation. It made me feel so smart because, I mean, look at it. That's a triple integration, and you have partial t in front of it. And look at this. This is the integration over the surface, and you had two vector dot product. Like, you write this equation in front of any of your friends that's not engineering, and like, wow, is this English? What is that?
No.
That's amazing. But this equation, actually, you never really use it in that form. We use it in much simpler form, but this is a more general form that can deal with any problem, right? This equation basically tell you that x, that property that we are tracking, whether it's mass or momentum, mv, or energy, not just kinetic energy, which include kinetic potential, internal energy, all energy, capital E. So that small e is not internal energy. That's the total energy per unit mass. Any one of those guys is x that we are tracking, right? And he's telling us that dx by dt system is basically this. Don't worry about this equation. What you need to worry about is the derivation of, or basically what this equation will end up generating. How does the continuity equation look like? How does the momentum equation look like? How does the energy equation look like? But I'm here to tell you that all of them are basically just a copy of that equation. We are just changing the x. I remember my Thermo 2 professor, 20-something years ago, telling us, if you want to be famous, you put this equation, try to come up with a new x that you put it in, and you'll be famous. Just come up with another x. I mean, someone put x equal mass, he came up with the continuity equation. Someone put x equal mv, came up with the momentum equation. Someone put x equal E, he came up with the energy equation. Try put another x in, right? So that scary part also, you know, because it's like dot product of two vector. All he want here is basically tell you that when the flow is coming in, the velocity and the area would be, the two vector will be against each other, because the area vector is always pointing outward of the control volume. So at the inlet, this is the inlet. V is coming in. If you dot product those guys, remember A dot B is AB cosine theta, where theta is the angle between the two of them. So basically this will just yield minus VA, the integration over the area. And when we are at the outlet and V and area are in the same direction, that dot product, you will have cosine 0, which is plus 1. So it will be plus. So basically this term will just be plus rho out, V out, area out, and it will be minus rho n, V n, area n. Alright, so all this just to get plus or minus. I mean, he could write plus or minus. No, it's because he also wants to tell you that it's only the velocity normal to the area that count. When it comes to m dot, when it comes to the flux, how much mass is leaving, it's basically the area normal to the velocity. So if the flow is moving with an angle, you take the normal area. You don't take the whole area. Right? This point is important when it comes to the oblique shock waves. Remember those things that was coming at an angle with the flow? So when we would like to come up with the actual flow rate, we shouldn't take this V and this area. We should basically take only the normal component. That's what really penetrates the control volume. It's as if we are dividing the velocity into two components. One that's parallel to the area, never will get n, and one that's normal to the area. That's what will really count. Alright? Okay? So this fancy form, I would encourage you to keep writing it to convince yourself you're really smart. It did work for me. I really like writing it. This will actually just boil down to this when you think about it. He's basically saying dx by dt system is, what's that? X rho dv. Rho dv, that's density multiplied by volume. That's dm. That's the mass of a small place inside the control volume. Multiplied by the small x. That small x is capital X over m. It's the x per unit mass. So if I multiply the x by all the mass, what do I get? All the x. So again, it's partial t x control volume, or basically the rate of change of that x. How much does the mass inside the control volume change with time? Is the compressor tank building up or depleting? So why all the trouble? Why he just could have said partial t x control volume? Because he was basically saying, in case you have a tank with different fluids, maybe you're working in a refinery, and that lower layer is like really heavy than the higher, you have different density. He basically telling you, well, each volume by its density, each volume by. So this is kind of the general form, all right? That will work for any problem. Of course, if the whole thing is one density, go for it. Just partial t x control volume. And again, this will just boil to partial x out plus x dot out minus x dot n. That's the rate. So now when you look at this equation, he's basically telling you that dx by dt system is the rate of change of that x inside the control volume plus x dot out minus x dot n. Don't even worry about this. We are not going to use it like this even. We'll get much simpler than that. Let's worry about the actual cases. When x is the mass, then dx by dt, the rate of change of mass with time for a system, is 0. Right? And those guys will simply be partial t m control volume plus m dot out minus m dot n. Or if we rearrange, it basically say m dot n minus m dot out. What's m dot n minus m dot out? The net coming in minus the net leaving. That's the net staying. That's the partial t m control volume. And you didn't need Reynolds to tell you this. You didn't need me to tell you this. If anyone with any sound mind will say, if there is 10 kilogram per second coming in and 8 leaving, you have plus or minus plus 2 kilogram per second staying in this classroom. All right? So what I'm trying to tell you is that this is the equation that you worry about. That's the control volume approach to solve the continuity equation. But this is the one that really makes sense when you think about it. And for most application, when it's steady state, even this term go to 0. And m dot n become m dot out. If there is no storage, and think about it, most engines are designed so that they wouldn't explode from us. Right, whatever come in need to leave. I mean, you had a problem if there is a blockage and nothing leave, right? So most problems, you just have m dot n equal m dot out. right? So let's solve a bunch of problem. So for example here, he's saying we had this tank, it's 100 meter cube, the temperature is 300 Kelvin, it's air, so 287, m dot n is 10 kilogram per second, m dot out is 2 kilogram per second. Obviously, the mass inside is building, right? And what does he want from us? He wants not just to tell him that dm by dt is obviously 8 kilogram per second, that's easy. It will be just writing this and say, well, 10 minus 2 equal this, and this guy, then it's 8 plus 8 kilogram per second. No, he wants partial B, partial T. He would like to find out what is the pressure, rate of change inside that volume. And he's saying the temperature is constant throughout the problem, 300 Kelvin throughout the problem. Is that a good assumption? Yeah, if the tank is really not insulated and that process happens slowly, you know, the tank will keep up with the ambient and he will remain at constant temperature. It's not a bad assumption. So how am I gonna get partial B, partial T? That's what he's asking for. So in this course, there is actually 3 equations: continuity, momentum, and energy equation. So when in doubt, when you don't know the answer, you have 30% chance of getting it right by just basically saying one of them. And since I just covered the continuity equation so far, chances are the solution will come from continuity equation. So let's write the continuity equation, which will basically say m dot n minus m dot out equal to, I need to make my pen a little bit bigger, equal to partial m partial t control volume. And so it's 10 minus 2, so that's 8. Well, that 8 is partial t m control volume. Right, so I did the continuity equation. Now, how am I going to get the pressure? How is that pressure he's asking for is related to the m, that the mass inside the control volume that we calculate? The density is V equal rho RT. What do you want to do with that density?
Well, you have your volume.
Excellent.
How many pounds are inside the tank.
Excellent. So partial T, that m is actually rho times V, rho times the volume, and that volume is constant. So actually we can bring that volume outside the differentiation, right? It becomes partial T of rho. And that density from the equation, ideal gas equation, rho then become B over RT. And notice that R is constant, that's the constant for air, and T is constant because he said this problem is isothermal. So I can take all those guys outside. And so it's volume over RT, and then all I have is partial B, partial T. All this is equal 8 kilogram per second. And so we have the volume, it's 800, I have the temperature, I have the rho, I got my hand on partial B, partial T. Ouch. Sorry. Alright? And so that's a cleaner version of this. It's basically tell you that partial T multiplied by the volume over R over T is equal to the difference between m dot in and m dot out. Right, question about this? So let's look at another one. So here's a rocket engine, he got his hydrogen and oxygen. The flow rate coming from this tank, the hydrogen is 2 kilogram per second, the flow rate coming from the oxygen tank, that's 8 kilogram per second, and the area at the exit of this nozzle is 0.3 meter and the density is 0.18. What does he want? He wants the velocity at this exit. So this is a combustion chamber where he dumped the fuel and the oxygen. And so let me ask you first, is this equation is unsteady so that I would write partial m partial t equal to m dot n minus m dot n minus m dot out, or is this problem steady state so that I could write m dot n equal m dot out?
It should be steady state.
Yeah, so this rocket is not steady, but the engine is steady state, right? The engine itself, I mean, the rocket is losing his fuel and oxygen, right? But the engine is steady state. That combustion chamber see a continuous flow of the fuel and oxygen and a continuous exit at the back. So because the problem is steady, because the problem is steady state, then, you know, when I was a student, I used to love to write always the equation from the start. Even if I know that, you know, it will boil down to m dot in equal m dot out, but it just gives me a chance to calm down while solving the problem, because I start with the equation that I know that it's never wrong. Because the general equation, that's the mothership, you know, that all the problem will come from that equation. And then I start canceling things from it. And also it really helps because if you have your hand or a good grasp of the full equation, you can solve different kind of problem. But if all you remember is m dot in equal m dot out, you may get lost if the problem is unsteady, right? So what I will encourage you to do is basically, before you even start that line, before you say it's steady state, I would encourage you to say, well, continuity equation is 0 equal partial t m control volume plus m dot out minus m dot n. That's the equation, continuity equation for everything, right? This also help in grading, because maybe you will screw up the rest of the problem, but if you wrote this one and this one is correct, you can always argue with the TA. Well, I had one equation right. I need 3 of 5, not 2 over 5, because one equation was right. You had a question. Someone had a question.
Yeah, it's 0.18 kilograms per second. Is it m dot or?
Say that again. This guy,
Yeah.
this is the density, rho 3. The density at the exit is 0.18 kilogram per second. The density at the exit, this is station 3.
The density is kilograms per second.
Sorry. Very good point. Kilogram per meter cube. Very good. Good job, guys. So now, since it's steady state, well, this guy will cancel, and we will end up with basically just m dot out equal m dot n. It's actually sigma m dot out equal sigma m dot n, not just one. If you have multiple inlet and multiple outlet, everything coming in should be equal to everything leaving. And so this then boils down to m dot 1 plus m dot 2 equal to m dot 3. And of course, m dot 3 is rho 3, area 3, V3. You have the rho 3, the 0.18 kilogram per meter cube, the area 3, you almost have it. You have the diameter. You know how to calculate the area, right? How to calculate the area from the diameter? Pi over 4d squared, right? And then you calculate the V that he wants, right? And so here's a cleaner version of it. He's basically assuming steady state and writing the continuity equation and then calculating the V3. All right. So this cartoon, I would just like to remind you that when we say rho EV to calculate the m dot, that V should be relative and should be normal. The normal part, we talked about this, right? We said that only the velocity component normal to the area that really goes through the area. There is this one country in Somalia, in Africa, that they have a lot of rain that actually come near the coast, but nothing really go inside. So as a result, the country is desert almost, because all the rain go barrel to the surface. Because the velocity component is 0, right? It's all barrel. So always remember this. If you're just moving barrel to the surface, nothing will go in the country. Nothing will go inside the control volume. So I'm basically saying, if you have a truck and someone is trying to hose you with water, only if the flow cross the boundary, you will end up getting water in the trunk, right? So what this mean? It means that if this car is moving at 10 meters per second and the water jet is also moving at 10 meters per second, Yes, there is a normal component. The whole thing is moving normal to the control volume. But if they are moving at the same speed, nothing will go inside. So that's why it's not just normal, but also it has to be relative. What does it mean, relative? So there is V absolute, and there is V relative. The V absolute is someone standing on the street, measuring the velocity of the water is 10 meters per second. A relative velocity would be someone standing on the control volume, measuring the cars, measuring the velocity of the jet. So there is an equation. You don't have to guess. Yes, it's 0, but you don't have to guess. The equation is V absolute is V relative plus V control volume. So if in case you are wondering what's V control volume, and you know this one, and in case you are wondering what is V relative, and you know V control volume and V absolute, all you have to do is say V relative is V absolute minus V control volume. So yes, 10 minus 10, you will end up with a 0. Right? So those two things are very important. It has to be relative, and it has to be absolute. Sorry, it has to be relative, and it has to be normal to the area. That's what make the velocity component that you will use in the continuity equation correct. You had a question.
Can you remind me one more time, why is it that we consider the rocket steady state?
So the rocket itself is not steady state. It's the combustion chamber. This part, the part that I highlighted with orange as my control volume that I'm writing the equation for. So what make it steady state? That I take a picture, say if I take a picture like this and then wait until tummy come out and then take another picture, that's not steady state. Something is different. But that combustion chamber, if I take a picture now, I take a picture after a few seconds, the combustion chamber itself doesn't have any change in it, right? So the mass of the control volume, which is a combustion chamber, not the whole rocket, is constant. Nothing gets stored, nothing gets depleted, right? So in short, if partial T is 0, that's what makes it steady state. Okay? For the problem, partial T is 0. Okay? So again, the velocity component that we should use here, it should be relative and normal. Alright, so in this problem, he's saying there is this nozzle and a shock wave like this standing. You can see the shock wave. We'll spend one chapter understanding what this shock wave is. But it's it looked, even in the picture, as a discontinuity in the flow. It's very, very thin. It's of order of magnitude of the mean free path. We are talking about, very, very small distance. And the flow behind it is one thing, Mach number 2, and the flow after it, Mach number 0.5. What happened? It's as if someone brought two things and patched them together. Okay? Like the new Honda Odyssey. Like you feel like someone brought two cars and patched them together. Exactly. There is a discontinuity after the second row, right? That's what a shock wave is. Basically just two different flow. And so what happened there, we will spend chapter 4 on it. But in this problem, he's giving us things at 1, and he's asking basically for the velocity at 2. All right? And this shock wave is so thin to the extent that area 1 is the same as area 2. So although, in real life it's like something like this, but no, it's not really. It happened over such a small area, such a small space, to the extent that area 1 is the same as area 2. So knowing V1, P1, and T1, and P2 and T2, he would like V2. How do you solve this problem? You know everything before, and you would like to know the velocity after. How do you solve a problem like this? B equal rho RT will only give you the density, right? Rho RT. This, we will use this to come up with rho 2. But where is the velocity? How can I get V2? The velocity after the shock.
Well, wouldn't you just set them equal to each other?
What equal to each other?
The two sides.
Yeah, what exactly on the two sides? You want to say what equal to what? Huh? Area 1 and area 2? That's what you...
The density as well. You'd have to do the density as well.
You want to tell me rho 1 equal rho 2?
Well, it's the mass flow is equal.
The mass flow.
So it's rho AB.
Right, m dot 1 is m dot 2. And let's ask ourselves why m dot 1 equal m dot 2? Who said this problem is steady? I want someone to prove to me that this problem is steady.
Persons,
Huh?
person says it's steadily flowing.
That means that this thing is standing in its place. But what I'm saying, why the mass is basically
Because the
not
only
increasing
thing
or
that can leave
decreasing.
is the only thing that is what comes in.
That's my question. Why? So what do you mean the area is the same? That's the right answer, but I want to put more words into it. What do you mean area 1 equal area 2? That's why the mass flow rate is the same as the mass flow rate. Because if area 1 equal area 2, that means I want someone to give me just a little bit more bigger statement than it's the same area, it's the same place, it's not moving. I want one more statement. It's steady state because the mass flow rate is steady state because what wouldn't make it steady state? What would happen so that it's not steady state and m dot n can be different from m dot out?
Collection.
A storage, a place for them to store the stuff, and then they can blow up or deplete. Why this will not happen this problem?
Because there's no place to store.
Because there is no place to store. Because area 1 is the same as area 2. Because that shock wave is so thin, there is almost no volume. There is no tank to keep stuff in. Right? So because of this, it's as if we are standing the inlet and the outlet at the same place. So of course everything coming in will also have to be everything leaving.
Does that mean that density 1 equals density 2?
No. No. See, the box that is so small that he cannot store, but still
It's like
the box is there and things happen inside. But it happens so quickly to the extent that we think of it as a discontinuity in the flow. But no, things happen inside that the pressure will, actually a shock wave is a huge change in the Mach number, the pressure and temperature. The temperature jump and the pressure change and the Mach number go from supersonic to, it's a dramatic change, but it happened over such a small distance to the extent that from continuity point of view, yeah, almost. Right, to the extent that when I say 0 equal to partial t m control volume plus m dot out minus m dot n, I am canceling this not because partial t is 0, it's really because m control volume is 0. It's as if there is no mass inside. Okay, so that's my take on it. After that, well, then the problem is easy. M dot out equal m dot n, and well, m dot out is rho AV, and rho out, rho 2, area 2, V2, and m dot n is rho 1, area 1, V1. And so we basically got everything at the inlet. The only thing that's missing at the outlet is the V2 and the rho 2. And that's when the rho 2 come. Rho equal BRT. Very good. All right? Questions? So here's what's going on. So he basically says steady state m dot 1 equal m dot 2, and he set the two equations together, and the only thing that's missing is V2 once he put his hand on the rho 2. All right, I'll let you solve this one. You have it in the notes. Conservation of momentum. So mv, that's momentum. So the dm by dt for a system, what's the rate of change of the mass of that iPhone? 0. He's not going to lose his mass, he's not increasing his mass. But the momentum of that iPhone could change, right? That iPhone could be standing like this and then he start moving. Why?
force.
Force. You give him a force, he increase his momentum. That's the Newton's second law, right? So the change of, remember here there was what? Partial dx by dt of a system, that's the force. So the forces acting will change the linear momentum of the control volume. What is the linear momentum of the control volume? There are momentum leaving with the flow, momentum coming with the flow, and the control volume itself could have its own momentum. It could be a rocket engine that's accelerating, right? Could it be a jet ski or something like that? It could change its velocity. It could add. So here is the momentum equation. Again, that's the fancy form that just look nice, but we will solve it in much easier form than this. I just want to tell you that this is actually not one equation. This is 3 equations. You see those vectors on the force and the velocity? That means that I can write this the whole equation in the x direction, y direction, z direction. Okay? So this is 3 equations, not 1. And we choose to write the one that's useful for us. We want the force in the x direction, we write the x momentum equation. We want the force in the y direction, we write the y momentum equation. Okay? So, again, the whole thing here is basically just mass time velocity in case the mass is uniform. So you will end up with mv control volume. And again, this over here, that's simply rho VA plus rho VA for m dot out minus rho AV for m dot n. So that's why you see plus m dot out and minus m dot n. And the small x that was here, now it's basically v, and here that's dx by dt, that's the force. So that's how the momentum equation look like. So now those velocity in here, not there's a velocity inside the m dot, and that velocity in the m dot, it has to be relative or absolute. The velocity that I used to calculate m dot as rho AV, that velocity need to be relative or absolute? Relative. Absolute. Not absolute. It has always to be relative. It has to be all the time relative. Because I remember again, if it's absolute, you may be making a mistake. 10 meters per second, and jet engine is moving at 10 meters per second, you would think, I have a lot of flow rate, but no, it's 0. It's relative velocity that counts. So now the second question is, well, how about that velocity here? Those 3 velocity, can they be relative or absolute? And the answer is, it doesn't matter. Either all of them absolute or all of them relative. Alright? You will get exactly the same problem, same answer. But sometimes it's easier to use one of them. For example, you know the relative velocity, or you know the absolute velocity, it was 0, to make your problem easier. But you should get exactly the same answer. Alright? The only trick is that if you are using relative velocity, here's a fancy word for you, that relative velocity cannot be relative to anything. No, it has to be relative to an inertial frame of reference. So that's a frame of reference that's not accelerating. Alright? So in the last lecture of the course, you forgot everything about this lecture by that time. I will basically give you the rocket equation, and then I will tell you, well, what velocity you should use here. And you would say, if you use relative velocity, that would be a mistake. Why? A rocket engine, we are tracking its momentum equation. Why we shouldn't use the relative velocity? Because that rocket engine is probably not moving with a velocity, uniform velocity. That rocket engine is accelerating, right? He starts from 0 at left off, almost 0, and then he shoots to a very, very high velocity to escape the gravity. So something like this is not inertial frame of reference. If you use velocity relative to him, you will making an error in the problem. So you would have to use the absolute velocity. You have to use the actual velocity with respect to someone that's not moving. Okay? But if the thing is moving with uniform velocity, then both of them works. But again, you have to treat all of them the same way. The 3 velocity at inlet, outlet, and the control volume should all be either uniform, either all relative, or all of them should be absolute. All right? Questions? So let's see some examples on this. So this is a rocket engine sitting on a stand. So then it doesn't really matter absolute or relative in this problem because the control volume is not moving. So the velocity relative to him or the absolute velocity is not moving. It's the same. Anyway, what he wants, he basically say that there is stuff leaving behind, hot gases at 800 meters per second. That's their pressure. Look at the pressure. It's 50 kilopascal. So it's not atmospheric. He can do this because it's probably supersonic. He can go with lower pressure than atmosphere. It can work. All right? It's possible. And area 2, that's the exit area, 0.01, and this is the mass flux. All right? So what he wants? He wants the thrust that will be generated on the test stand holding the thing. Right? So what equation should I use? Continuity equation or momentum equation? No, when we ask about forces, it has to be momentum equation. See, the momentum equation got the force into it. And only the x direction, right? We don't have to write the y momentum equation. Actually, when we write the y momentum equation, we will get 0 equals 0. I mean, there is no force vertically generated, and there is no velocity in the vertical direction. Everything is leaving horizontally, right? So what I'm saying here is that step 1, before you write the momentum equation, before you try to calculate the force, step 1 is no. Decide what is the plus direction. Any vector equation, even if we are saying we are writing only the x momentum equation, forget about the y and z. But even in the x, the force can be plus 800 Newton or minus 800 Newton, depending on are you in the x direction or the opposite x direction. The velocity, those velocity over here, you will not write 800 meters per second. This has to be minus 800 meters per second or plus 800 meters per second. What will decide plus 800 or minus 800?
Your sign.
It's this guy. And so you can make it to the right or to the left. It doesn't make any difference.
Just stay constant with it.
But you stick to it, right? You stick to it when it comes to the velocity, when it comes to the forces. All the vector quantity. Of course, when it comes to m dot, it's not there. There's no sign. Right? But the velocity and the force need to basically be to follow that plus direction. So the first step is to decide this is the plus. I'm going to take it to the right. The second step is to start putting the forces acting on the control volume. So the control volume is my rocket. So he will feel a force from the stand. Right? I mean, that rocket engine is actually pushing the stand. But because the stand doesn't want to move, otherwise you're in trouble if this thing starts moving, right? Actually, this happened one time, the tank, and it get broken, and it was like a rocket engine, and this thing start flying in the factory basically, and they really knocked a bunch of walls in the way. So if the stand is strong enough, he will put force equal to the thrust. You know, they test jet engine by putting it in a stand. That stand need to build enough force equal to the thrust that engine generates. That's how they measure the thrust, and they say, test was successful, we generated 800 whatever pound force. All right? 8,000 pound force. Anyway, so that force, what I'm trying to say is the force on the control volume. All right? So if we calculate this equation like this and find out that the thrust is plus 8,000 pound, is that correct or false? That the thrust actually not that it's plus 800, the fact that it's in this direction. That's correct, right? That's the force that the engine, the control volume would feel, right? Because you know probably now that the engine actually will move the stand to the left, right? And therefore the stand will have to put a force to the right, or a plus force on the rocket engine to keep it in place. All right. So it helps, you know, that we will get the sign that we expect. That when you solve this problem and you look at the number, you say, oh, it's good, it's plus 800. I was scared it would be minus 800. Then you know that you screwed things up. Okay. The second part is, we are still in the second part. We are putting the forces. So here's the thrust. Any other forces that I need to put? The thrust and I put the thrust already. That's the T. That's the force from the stand on the control volume. Any other forces acting on that rocket engine?
Atmospheric, but
The pressure forces, not just atmospheric pressure. The pressure forces all over it. So yes, everywhere here it's atmospheric. And at the exit, it's the B2, area 2. But I don't want to worry about the B atmosphere because I don't even know this area. I don't want to worry also about the X component and all this mess. So rather, I will just use B2 gauge area 2. All right? And then over here, it's like 0. No atmosphere pressure. It's taken care of by saying B2 gauge area 2. Right? What is this ball with rocket, with arrows flying out of it? Can anyone guess?
with what?
What is this ball with arrows flying over it? What's that?
Explosion.
So this is my answer. See, this is actually every year a lot of students, after I solve this problem, they shout basically or complain that why you make B2 gauge area 2 like this to the left. Those gases are leaving, not coming in. They are leaving the engine. Why you are putting the pressure to the left, not to the right? They should.
Actually pushing the rocket.
Right, because we are putting the forces on the rocket, on the control volume, from those guys leaving. So what is the pressure force? So you need to understand the pressure force. This wall in this classroom, they have atmospheric pressure on this wall, on the ceiling, on the floor. Every one of them, and if the pressure here is big enough, you know, if we build the pressure, if everyone like really push a lot of air, and this room would basically explode outward. Everywhere it will explode outward because of the pressure. The ceiling will go up, the floor will go down, right? If you can imagine that. And the walls will burst. So the pressure is basically will always try to push on the wall outward. Why? Where is it coming from? The pressure, we said the air molecules are a bunch of spheres bouncing around, right? That's it. They are a bunch of spheres bouncing around. So how does it generate the pressure, the force per unit area? The 100 kilonewton per meter square. Every meter square here get 100 kilonewton. Where is it coming from?
It's pushing on the air on the outside.
It's coming from those billiard ball hitting the wall and bouncing back, right? So you know, if I hit you with that pen, it will hurt. But if I hit you and it bounces back, it hurts you even more. That's, you get 2 MV, not just 1 MV. That change in momentum, because the momentum is a vector direction, a vector quantity. So plus MV, minus MV, that you can try it at home with your so you hit the head and bounce back, and that's what happened per unit per collision. And so now you can calculate, and they do this in grad school. They basically calculate the pressure as function of the kinetic energy of this molecule. They calculate how much flux or how many molecules per unit time, per unit area hit the wall and come back. And then they end up basically saying, well, the pressure then is rho RT. It's amazing when you think about it that you can correlate that kinetic energy to eventually become rho RT, right? So because the T is just a measure, there is a relation between the temperature and how quickly they are moving, right? So my point is, the pressure is simply the collision of the molecule with the wall. So of course, that area that we would like to calculate the force on it, now let's clean ourselves. It's because simply those molecule outside. So those molecules outside will not hit your area and then pull you with it, right? There is no way the molecule will hit the wall and then take a piece of the wall with him leaving. No, he push it and he push it forward. All right? So that's why the pressure is basically, in short, pushing on the control volume, right? That's the B2 gauge. And all those arrows was basically, I was trying to tell you that the pressure of all those molecules is outward with respect to them. Those guys will push the floor down, the ceiling up, every wall around them, away from them. All right, we are done. So we put the plus direction, we choose it. We put all the forces, which turn out to be just the thrust and the pressure force, and now we are ready to write the momentum equation. All right, so the solution, that would be the y momentum equation, or the x the momentum equation. This is the y and this is the x. I should write x momentum equation. And so the x momentum equation would be plus t, and why it's plus t?
Because it's in the plus direction.
I choose that, right? It could be minus t if someone choose the plus direction in the other way. Minus B2 gauge area 2, and you know why minus? Obviously, because that's the direction. Equal to, sorry, partial t, m, v, control volume, and I'm going to set this to 0. Why? No, not really steady state. That rocket engine is not steady. That rocket engine, see, the control volume is the whole, unlike that previous small problem that we had where I had the control volume on that combustion chamber, and I told the combustion chamber is steady. Now I'm basically saying the whole thing sitting on the test stand is my control volume. So this guy is losing mass.
No volume or velocity.
Yeah, the
No velocity, excellent. It's because the velocity is 0. He's not moving. Right? So now you can imagine if this guy start moving, that equation will be different. Right? Plus m dot out, v exit, which is v out, and I would like to say plus v exit, where this is v exit. And why plus v exit? Because it's in the plus direction. Minus 0. Why 0? Because there is no m dot n. All right? And so then the thrust is m dot out, v exit, plus B2 gauge area 2. So here's a good trick that I used to do when I was a student. I used to actually, even with the problem the number are given to me, I wouldn't substitute until I get the final equation. Then I put the number. I mean, we could have put the pressure here in this place, right? But no, I would keep the number until the end. Why did I do this? Well, first of all, it's easier to keep the symbol while you are flipping the page and going from line to line than the number. Number are very easy, you can screw them up. Second, when you keep the symbol like this, you can check the units. You can check dimensions basically, and then that allow you to figure out, did you drop an area in the middle or right? So here, what is the unit of B area? Pascal or Newton per meter square multiplied meter square. That is Newton. Newton thrust must be Newton, and if you check the kilogram per second times meter per second, you will figure out that it's Newton also. Why? Because it's mass times acceleration, right? You will figure that. So having it in symbol like this will allow you to basically check the dimension. And you learn a lot actually. I used to spend a lot of time after solving the problem just looking at this and trying to make sense. Does it make sense that the result is not 800 plus 700? You don't figure what's going on, 800 plus 700. But when you look the number like that, the symbol like this, you'd say, so the thrust is coming from two things. One thing is the momentum I'm throwing behind, m dot v, and the other thing is the pressure that's there. All right? So this rocket is being pushed forward because of throwing stuff behind and because the pressure building behind him. right? And also it really makes sense to check the sign that it's plus m dot out v out plus b dot gauge area 2, meaning the two of them are helping each other. It's not like one of them is subtracting from the other one. One of them is pushing while the one is pulling. And so, does it make sense that they are helping each other? Yes, because pressure behind you, that will send you forward. Assuming, of course, P2 gauge is plus. It's 120 kilopascal, and therefore P2 gauge is plus 20, not minus, and then it's pulling you, not rather than pushing you. So the fact that this guy is behind you, that will push you. The fact that the velocity is leaving like this, that also pushes you forward. All right? Question about this? Right, so here's the cleaner version of it. He's basically writing the momentum equation, setting this guy equal to 0, and therefore the thrust is... So this equation is so famous that basically later when we go rocket engine in last chapter, we don't write the momentum equation and say this velocity is 0. People actually just simply write this. M dot out V out plus B dot gauge area 2. All right? And then one of you should ask a very good question right now. That question should be, well, why this equation is useful? You just said that this is only when this guy is not moving. What if the rocket is actually moving? This equation shouldn't be useful.
That's constant. The thrust force is constant.
Well, it will turn out that we will make two mistakes that will fix themselves. So it will end up being exactly like this too. But you will see later on. So this equation, I'm telling you, this equation is really useful whether this guy is moving or not. All right? So the two mistakes will fix each other, and you will end up with, here is the thrust. It's two parts. Part momentum and part pressure. All right? Got it? So the last part in this conservation of stuff is conservation of energy. That's the first law of thermodynamics. And again, this equation, first law of thermodynamics, it's exactly the same equation like before, the same momentum equation, the same continuity equation. The only difference is that now that x that we are tracking is the E, this is the energy, total energy. And so does this room, this control volume, can change its energy content? Yes, it can, right? To start with, there can be energy in from those ducts. There could be energy out from the doors, right? And also there could be energy added and work done on us. There could be like ceiling fan here that will send work in, or can be energy added by heat transfer from the wall, or internal energy. You know, if you think really hard, you can get hot and then that generate even extra energy. So Q dot minus W dot, that's basically the, and here's the difficult, or not difficult part, the confusing part is that when you add Q, that's plus. When you take work, that's plus. And when you think about it, why they just didn't make anything you add is plus and anything you take is minus, right? Probably historical reason for power plant where they used to add fuel and then they take work out of it. So they didn't want to keep saying, this power plant is perfect. We generate minus 100 kilowatts. I mean, they didn't want to say minus 100 kilowatts. So they said, no, if we get work, that's plus. If we add Q, that's plus. Some thermo textbook actually say, no, forget about this. You add, it's plus. You take, it's minus. And therefore, the law there would be not Q minus W. It will be Q plus W. All right? Anyway, so this net energy in, so Q minus W, that's the net work being added to that control volume. That could actually change the energy content inside this control volume. This is partial T, energy inside the control volume. And this, again, the whole thing here is m dot out minus m dot in multiplied by the energy leaving and coming. So one weird thing, however, is that when it comes to the flux leaving or coming in, you multiply m dot by h plus half v square plus gz. That's potential energy per unit mass. That's kinetic energy per unit mass, and that's what's h? Enthalpy. But when it comes to the control volume, how much energy is inside this control volume, not the inlet or the outlet? Potential energy, okay. Kinetic energy per unit mass, okay. But only internal energy, U, not H. What's the difference between H and U? This guy, B rho. Or basically you can say that it's U plus PV. So the difference between H and U is PV, or we call it the flow work. For a reason that I'm going to explain in a second. So he come with enthalpy, but he stay with internal energy, and then he leave with enthalpy. Why is that? Why he, when he's inside, what happened to his enthalpy? So here is why. So remember, there are pressure forces standing outside, PA and PA, right? That's a pressure force at the inlet and pressure force at the outlet. So if consider a small volume of fluid trying to leave, there is a pressure force in front of him. So you need, in order to get him out, you need his friends to push him so that he can take that work and leave. That's exactly that two forces. So the work done by a force, you basically have to say it's the force multiplied by that delta L. And then eventually it comes, so that's the force, that's the work. So the work per unit mass, you divide over the mass, dV. Right? So what's the volume? It's rho dV. That's the mass, sorry. So you got B delta area multiplied by delta L. So delta area cancel with delta V, and then you eventually figure out that it's P over rho. So the work per unit mass, which by the way, all those guys are per unit mass. H, V half V square, GZ, what are the unit of all those guys? What's the unit of the enthalpy? Anyone? The units of the enthalpy?
Kilograms per meter.
Enthalpy, when you open the steam table.
Joules per volume.
No, joule per
Energy per mass.
per kilogram. It's energy per unit mass. The work also per unit mass is BV. So, but this is work. It should have been done here. And so they used to put it there in this term because that's work done, right? But it's not really useful work. We never really see it. We never, the engine or the power plant, never actually see that work, right? So because of this, they said, well, let's keep this term only for the useful work. A fan, a turbine, a pump, and let's move that flow work and put it here together with U. Perfect. U plus PV, so it turned out to be enthalpy. Right? So that's why when you are dealing with a system, if you have a cylinder in your design project, and that system, that cylinder, basically you are expanding it so that you are pushing something, you will never have enthalpy. You will have internal energy. But if you have a pipe where things come in and things leave out, they come with their enthalpy and they leave with enthalpy. And you know why? Because you don't want to calculate the work that you need to spend to get them out. So you basically tell yourself, they are leaving with enthalpy. Or basically to leave, they have to get this extra energy to take the pressure force in their face that will hit them if they try to come out. Okay? Got it? Alright, so no mystery. It's he leave with enthalpy, and when he stay in, he stay with his internal energy. So again, that is the fancy form, but the simple equation is basically simply this: Q minus W is how much internal energy plus kinetic plus potential you have, plus m dot out, H plus half V squared plus GZ, minus m dot N, H plus half V squared plus GZ. Right? And if the problem is steady state, which most problems are, simply then Q minus W is m dot out, H out, minus m dot N, H in. And actually, when you look at the compressor or a turbine or anything where energy is coming in and energy is leaving and there's Q and W, you didn't need all those 5 minutes for me talking about this. You could immediately say, you know what, forget about plus Q and minus. I will just say energy in equal energy out. And you basically say, well, those guys come in, those guys leave. So at the end of the day, Q plus, so this is Q. At the end of the day, Q plus M dot N, energy in equal to work plus all the energy out. Done. And so if you ask for the power or how much heat transfer across the wall is happening, anything in this problem is asking for, you basically fill in the gap and finish the problem.
So you're fine with this, just writing it in that form?
So again, this equation really, if only for steady state. If the problem is unsteady, maybe you have to add this term, right? The unsteady term. But if the problem is steady state, yes, you start with here. Right? Questions?